Bismillahirrahmanirrahim. In this tutorial, we'll talk about the ideal gas and continue talking about the ideal gases. And we'll introduce or talk about two new topics: the air conditioning, changing the air conditions like changing temperature and pressure, and we'll talk about the chemical reactions in ideal gases. So up till now, we were just talking about a single gas or maybe a mixture of gases, just physical mixing, without any reactions happening between the gases in that mixture or any change in number of moles. Today we'll extend our studies to chemical reactions that could happen or could take place in a gas mixture, resulting in a change of number of moles and introducing different gases into the system. All right, and we'll continue, of course, solving sheet 1. So the first topic or concept to talk about will be relative humidity, and this just refers to the amount of water vapor in a gas relative to the saturation amount of water vapor at that temperature. Okay, so let's say an air is saturated with water vapor. This will be saturation pressure over the saturation pressure, which will give 100%. This is 100% relative humidity. But if the gas could contain up to, like, let's say 30 millimeter mercury of water vapor, and we only have 15 actually present in that gas, then the relative humidity for that gas is 50%. Okay, so it's just a scale to tell us how much the air or the gas is saturated with water vapor. Right. Moving forward, the air conditioning is just changing the air conditions like temperature and pressure, which of course results in the change in relative humidity. Since the relative humidity is dependent on the temperature of the gas, how much the gas could absorb or take water vapor at that particular temperature. Changing the temperature will of course change the saturation pressure. So even for the same number of moles, the saturation, the relative humidity for that gas will change. Okay, so if we have an air conditioner that changes the air conditions, and we introduce a gas or air into it in a stream with V1, T1, P1, and the saturation at T1 for water vapor, and then the relative humidity, we can calculate the relative humidity knowing that the P of water or the partial pressure of water vapor that's actually in the air mixture, we can get the relative humidity inlet into the air conditioner. And changing the conditions for that air will get a different volume, temperature, pressure, and of course, since the temperature changed, the saturation pressure for water vapor will change at that temperature. And this water pressure could change depending on the changes that happen inside the air conditioner. And then there could be condensed water if the relative humidity here was to exceed 100% relative humidity, so the gas will not be able to maintain the same amount of water, and will start condensing some water as liquid water in here. So let's say when we entered the air conditioner, we had 8 moles of water, and the saturation for the air was 10 moles. So we had like 80% of relative humidity. And let's say at the temperature and pressure, the new temperature and pressure, the saturation for that temperature was just 5 moles of water in the entire mixture. So these 8 moles of water will not be able to stay in the vapor phase. Only 5 of them will be in the vapor phase, and the remaining 3 will need to be condensed as liquid, since the gas at that particular temperature cannot contain any more water or dissolve any more water in the vapor state. Okay. All right. Let's solve a couple of problems to see how this works in action. The first problem says a closed chamber of volume 100 meter cubed, the volume, contains atmospheric air at 40 degrees Celsius, and the relative humidity of 80%. So percent relative humidity 1 is 80%, and the pressure, P1, is 754 millimeter mercury. Was cooled down, so this is the temperature going out from the air conditioner. Calculate the pressure change inside the room, and calculate also the amount of condensate water. So if any water condensed in the air conditioner unit, we need to know how much water was condensed. Okay, so first off, drawing the system, we have all the conditions entering the air conditioner, and we have the conditions going out. We do have the volume, since it's the same room, so the air conditioning is just taking the 100 meter cubed of air, conditioning them, and then returning them into the room. So the volume remains the same. The temperature is dropped from 40 degrees Celsius to 25. We don't know the pressure, but we need to get the pressure drop or pressure change, which is delta P, the P1 minus P2. How did the pressure change? Okay, and we have the saturation pressure. This is not to be memorized. We can actually get this from the table that we discussed in our last tutorial. And then the P water 2, since in the problem itself it says we need to calculate the amount of water that got condensed, then we know that the relative humidity out of the air conditioner will be at 100% to be able to condense some water in here. Okay, so we know that from this statement, we know that the water pressure in the outlet gas is the same as the saturation pressure of water at the same conditions or at the same temperature. All right, let's solve. So the P water 1 is 80% relative humidity times the saturation, which we got from the table. And the P dry gas is just the total pressure minus the water pressure, partial water pressure. And why do we get the dry gas pressure? As we mentioned before, to use the shortcut relations, we just need to know that the gas is the same amount of moles going in and going out, or in the two states. And since we have the only thing that would be changing number of moles is the water, so we just take it out from both sides to know that oxygen and nitrogen will never condense at these conditions. So we just work with the dry pressure of oxygen and nitrogen. Okay, and for the conditions for the outlet, we can get P water 2, and we can get the dry pressure by saying P1 over T1 equals P2 over T2. But this will be the dry pressure, since the number of moles needs to be constant for only the dry component of the air. And to get the total pressure, P2, we just need to add the partial pressures according to Dalton's law, and we get a total pressure of 700 millimeter mercury. So the pressure drop will be the final pressure minus the initial pressure, which is 700 minus 754, and the pressure drop is just minus 54 millimeter mercury. Okay, so pressure 2 is actually less than pressure 1 by 54. And to get the number of the amount of condensed water, we can just apply the ideal gas law for the water that was inside the inlet gas and the water that's inside the outlet gas, and subtract both to know how much water was condensed. So applying the ideal gas law two times, once for the inlet and once for the outlet, we get N water 1, N water 2, and the water condensed will be just the difference between the inlet and the outlet of water vapor will give us the liquid water condensed in that AC unit. All right. Okay, the second problem says air at 40 degrees Celsius and 80% relative humidity and 744 millimeter mercury was compared to a volume of 2.5 meter cubed at a total pressure of 1700 millimeter mercury, and temperature 42 Celsius. So this is P2 and T2, and this will be T1 and P1. Okay. All right. Calculate the volume of air before compression. This is V2, and we want to know what is V1. All right. And the weight of the condensed water that may occur in the process. So this statement doesn't tell us if there is condensation of water happening or not. It just says if there is a condensation process taking place, then calculate the amount or the weight of condensed water. All right, and we're given the saturation pressure for water at both temperatures. Right, so drawing the system, getting all of the parameters we have. This time we don't know the relative humidity here, and we don't know the water pressure, since we don't know if any condensation took place or not. Right, so how to solve this? We will first assume that no condensation took place. All right, and we'll just work directly with the relations. Assuming that no condensation took place, then the total number of moles before the air conditioner is the same, including the water, since no water was condensed. All right, so we get the volume 1 from this relation. Then we use that V1 that we got, the volume before compression, to apply the same rule again, but this time only for the water, and we calculate the water pressure in the outlet gas at that volume. What would be the water pressure? So this is the water pressure that would be in the outlet stream if no condensation took place. How do we know if the assumption is valid or not, or is it correct? We need to compare this water pressure in the outlet stream with the saturation pressure. If it's over that saturation pressure, then this means that the assumption is wrong, and condensation needs to take place, because this way the air is oversaturated with water vapor. It only can contain 62 millimeter mercury of water, but according to our assumption and calculations, the air would contain over 100 millimeter mercury. So this is not valid, and this tells us that this assumption is wrong, and a condensation will indeed take place. So what do we get from that? We know this time that the relative humidity in the outlet stream will be 100%, and hence the water pressure in the outlet stream will be the same as the saturation pressure at 62 millimeter mercury. All right, and we'll continue working on this time on the dry components of the gas or the air to work on this relation. Instead of total pressure, we'll work with the dry pressure. So we get the total volume before compression, and then to get the number of moles of water in the inlet stream, we just apply the ideal gas law, and same goes for the outlet stream. And then to get the total weight of water condensed, we need to first get the number of moles condensed, which is 5.6 gram moles. And to get the total weight, we just multiply that by the molecular weight of water to get the final answer. All right? Okay, moving forward to our second topic, the chemical reactions in ideal gases. If we have a reaction on this general form, X amount of A reacts with X amount of Y amount of B to produce Z amount of C. As an example, nitrogen and hydrogen reacting together to produce ammonia. And if we have inlet amounts, different inlet amounts of the nitrogen and hydrogen gases to produce ammonia, and at the very start, of course, of the reaction, we still don't have any ammonia present in the system, we need to know first, to be able to quantify and work with this reaction, we need to know the limiting reactant in this reaction. And the limiting reactant could be retrieved just by dividing the number of moles, the actual number of moles in the system or in the reactor, over the stoichiometric coefficient, which is just 1 for the nitrogen, 3 for the hydrogen, and 2 for the ammonia. So to know which will deplete first or run out first, we just divide the 100 by 1 and the 500 by 3. And it's obvious here that the 100 moles of nitrogen will react with 300 moles of hydrogen, and there will be an excess of 200 moles of this hydrogen present in the system even after all the nitrogen is depleted. So this nitrogen is the limiting reactant for us, and everything in this equation will be represented as a function or in relation to this limiting reactant quantity. Okay, so for a certain conversion or reaction amount of this limiting reactant, 3 times of that X amount will be reacted, and this is why the minus sign in here, will be reacted or depleted from the 500 moles that were introduced into the reactor. And for this amount X, the produced amount of ammonia will be double that amount X. All right? And at any point in the reaction, after X amount is reacted, the remaining number of moles for nitrogen, hydrogen, and the produced ammonia will be just the 100 moles that were originally introduced, the initial number of moles, minus the amount that reacted inside the reactor. So 100 minus X. Same goes for the hydrogen. Initially, there was 500 moles of hydrogen, and minus 3X reacted with this X of nitrogen to produce this 2X of ammonia. Right? So the conversion percent is just the reacted, which is in this case this X over the inlet amount of the limiting reactant, which is the 100 moles in here, and we can calculate it as this expression. And the total number of moles at any point in the reaction, at any given conversion, is just the sum of all the present or outlet number of moles here. So in this case, in this particular case, it will be 100 plus 500 plus 0, which is just 600. This is in total. Minus X minus 3X plus 2X. So it will be, this will be minus 2X. Okay? So the total number of moles as a function of the conversion at any given point will be 600 minus 2 times the amount that was converted from the nitrogen. So at the very start of the reaction, this is 0. So the total number of moles will be 600, which is just the sum of these two together, the inlet amount. And let's say when the total amount of hydrogen present is reacted, so 100 moles of nitrogen reacted. So this will be 600 minus 200, which is 400, which will be just 200 moles of ammonia produced and 200 moles of nitrogen, hydrogen that were in excess in the system to start with. All right? So that's at the very end of the reaction, if 100% conversion was obtained for the total mixture as a function of X based on this relation. All right? So let's solve a couple of problems to practice this. The first problem says quicklime calcium oxide is produced through thermal decomposition of limestone, which is calcium carbonate, as we discussed before in cement production. Calculate the volume of carbon dioxide produced at STP from the decomposition of 152 grams of calcium carbonate based on the following reaction. So this is the following reaction, the thermal decomposition of calcium carbonate into calcium oxide solid and carbon dioxide gas. And the amount of moles present in the system initially was 1.52 gram mole. So if we build the reaction table for this particular reaction, 1 mole, this is just the stoichiometric coefficient, 1 mole of calcium carbonate reacts or decomposes into 1 mole of calcium oxide, and also 1 mole of carbon dioxide. So if we initially in the system have 1.5 moles of calcium carbonate, this means that we will get 1.52 moles as well of carbon dioxide when this is completely reacted or completely decomposed. And to get the volume, we can just use the ideal gas law to get the volume of this carbon dioxide at STP. All right, so that's all we need to do when taking chemical reactions into account. Next problem says N2O4 gas is typically produced using the following equilibrium reaction. So this is a reversible reaction here, which just says that N2O4 reacts to get NO2 or the reverse. Calculate the conversion percentage of N2O4 to NO2 if we found 24 grams of the gas mixture at 15,000 centimeter cubed or 15 liters, volume and temperature and pressure. Okay, so the initial amount is just those 24 grams for N2O4. We can get N initial is 0.26 gram moles. All right, and if we build the reaction table, the inlet of N2O4 at the very start of the reaction is 0.26 as we got here, and NO2 is just 0. We're still starting the reaction. And for any amount X of N2O4 reacted, we get double that amount or number of moles for NO2. And at any point, as a function of X, the total number of moles remaining would be the inlet minus the reacted for each component for the reactants, and for the products will be the inlet plus the produced inside the reaction. So the total number of moles from this expression here, summing these two together, will be just 0.26 plus 1x in here. All right. And the total number of moles at these conditions from the ideal gas law, we can easily retrieve that as 0.49 gram moles. Substituting by this or this number in here, we get X is equal to 0.23 gram mole. All right, so we don't need just to get this X value, we need the conversion percent from the initial amount of N2O4. And the conversion is just, as we mentioned before, the amount that reacted from or over the amount that was initially introduced into the system as a reactant. So 0.23 gram moles that reacted here over the 0.26 gram moles that started the reaction, which is almost 90% conversion. All right, next problem. In an experiment for ammonia synthesis, the initial volumetric ratio of hydrogen to nitrogen was 4:1. After ammonia formation, the ratio, this ratio was found to be 4.5:1, the exact ratio of hydrogen to nitrogen again. Calculate the partial pressures of all the components in the final gas mixture at 770 millimeter mercury and 727 degrees Celsius. That occupies 50 liters. Okay. So building our table, if the inlet of nitrogen is Y, the hydrogen will be 4 times that amount of nitrogen, 4Y. And of course, starting the reaction, there is no ammonia in the system yet, unless it's specifically mentioned in here that there was ammonia in the gas mixture starting the reaction. All right. And to get the total number of moles at any reaction extent or amount X, we can just say if X amount of nitrogen was reacted or consumed, this will react with 3 times the X here of hydrogen, and will produce 2 times this X amount reacted as ammonia. So the total number of moles at the very end will be the summation of all this, all these quantities in here. All right. So the other given in this problem was that after the reaction, the ratio between hydrogen to nitrogen, NH2 over N2, was found to be 4.5 to 1 instead of 4 to 1 as the inlet here. So what's the amount of hydrogen as a function of x? It's just this one, so 4y minus 3x. And what's the amount of nitrogen? It's just this one, y minus x. And from this expression, we get a relation between y and x. Let's call this relation star. And n total would be 5y, just the summation here, 5y minus 2x. This n total, from the final conditions to the of the mixture, pressure, temperature, and volume, we can get this n total value in here, and would be 0.6 gram moles, and this will be called our relation, second relation, or double star. And from both these relations, we have two relations and two unknowns, x and y. We can calculate the x and y. All right. We don't stop there. What's required is to calculate the partial pressures of all the components in the final gas mixture. So this is easy, of course. We can just get the molar fraction for each of the components, nitrogen, hydrogen, and ammonia, and multiplied by the total pressure in the final gas mixture. Okay, so that's the pressure of nitrogen, pressure of hydrogen, and pressure, partial pressure of ammonia. That's it for today's tutorial. Please let me know if you have any questions anytime. See you next time. Cheers.